Picture a distance map of galaxies in the direction of Boötes. And the question is why one enormous part of that map contains so few galaxies that people began calling it a hole in the universe. Nothing has punched through space. Nothing is missing from reality. The Boötes Void is an underdense region, a vast place where the galaxy crowd thins far below the cosmic web around it. But that correction does not make the mystery smaller, it makes it sharper. If gravity builds structure across the universe, why does one famous region become such organized absence? By the end of this video, you will understand how the Boötes Void turns from a scary-sounding hole into one of the clearest maps of cosmic web architecture. So settle in with the question, not the legend. We are going to follow the evidence from a missing crowd to the physics that lets absence have shape. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. A telescope does not point toward Boötes and see a round black object. That picture is too simple. What astronomers found was quieter and more powerful. A region where the expected crowd of galaxies did not appear on the map. Now think of a city map. Downtown has streets and buildings. It has addresses too. The motion only makes the crowd easier to notice. Then imagine one district as large as a small country, with only scattered houses where neighborhoods should be. You would not call that a wall, you would call it a shortage. The Boötes Void begins with that kind of shortage. The evidence is comparative. Around it, galaxies gather into larger patterns. Inside it, the density drops. The drama is not that space turns off. The drama is that the distribution changes over a huge scale. But we need to be careful with the word visible. The void is not visible the way Saturn is visible, or the way a nebula is visible. It appears only after many galaxies are counted and placed. We see it because a pattern refuses to fill in, and that matters because a missing crowd is not the same as nothing. If you walk into an auditorium built for 10,000 people and find a few dozen scattered across the seats, the room is not empty in the strict sense, but the event has clearly not filled the room. So the first clue is not a photograph of darkness, it's a census. How many galaxies should a volume like this contain if it resembled its surroundings? How many do we actually find? The gap between those answers is where the Boötes story begins. We can feel the scale only by slowing it down. A light year is already enormous. It's the distance light travels in a year. The title phrase, roughly 300 million light years, is not a tidy measurement of a shell. It tells us this sparse region is not local, not small, and not a minor gap between two galaxy groups. But no honest map draws a sharp rim around it. The edges soften, the density rises gradually, the surrounding web becomes more crowded. Somewhere in that change, astronomers draw a boundary for analysis. The boundary is useful, it's not a wall. Here is the first clean handle. Boötes is famous because galaxies thin dramatically across a vast mapped volume. It's not famous because a camera discovered a cosmic cave. Look at the word hole one more time. In ordinary life, a hole has an edge and an empty center. In cosmology, this case is different. The word is shorthand for a statistical fact. Compared with galaxy-rich regions around it, this region is poor in galaxies. That may sound less dramatic until we ask what galaxies are doing in the first place. They are not sprinkled randomly like glitter. They trace gravity and dark matter. Gas matters too. Time turns those ingredients into structure. When a large region has far fewer traces, it tells us something about the pattern underneath. And the pattern underneath is the real subject. The Boötes Void lets us study not only where matter gathered, but where matter did not gather enough to make a normal galactic crowd. Now imagine holding two transparent maps over each other. One shows a busy strand of galaxies, the other shows Boötes as a pale opening beside that strand. The important feature is not the darkness by itself, it's the contrast. We need that contrast because the universe has no painted labels. Nobody marked the boundary for us. Astronomers infer it by counting galaxies, measuring their distances, and asking whether the region behaves like the average cosmic neighborhood. So our first answer is plain. The so-called hole exists because the map shows a dramatic shortage of galaxies. But that answer immediately opens the next problem. A shortage on a flat sky can fool us if we do not know distance. The map has to become three-dimensional before the absence can be trusted. But we also need to notice what the census does not say. It does not say every part of the region is equally sparse. It does not say the same galaxies would be found by every survey. It says that across the mapped volume, the expected population falls dramatically below the nearby cosmic web, and that is why a map can be more dramatic than a photograph. A photograph can seduce us into imagining a dark object. A map forces the better question, compared with what? Density always needs a reference, and once we have that reference, Boötes stops being a blank in the sky. It becomes a measured contrast between neighborhoods in the universe. Another useful way to picture the first evidence is a library shelf. If one shelf has thousands of books and the next shelf has only a handful, you do not need a ghost story to notice the difference. You need a count, a comparison, and a reason to trust the shelf labels. Galaxy surveys begin to provide that. They let astronomers ask whether an apparent quiet region is truly sparse. Maybe the galaxies are too faint, maybe they sit beyond the chosen sample. The method has to test those possibilities before the word void can carry weight. Boötes became powerful because the shortage persisted strongly enough to deserve attention. The map did not merely show a small break in a strand. It showed a broad region where the usual galactic crowd faded. But we should keep the listener's eye on the evidence. The void is not an object added to the universe. It's a pattern extracted from many objects. Every galaxy position is a small mark in the argument, and if the marks are missing across a large enough volume, the absence becomes measurable. Not because nothing exists there, because the expected traces are dramatically fewer. Now imagine a surveyor walking a huge field and placing flags wherever a galaxy is found. In most directions, the flags cluster into lines and knots. In Boötes, the flags become sparse. The field itself remains real. The pattern of flags changes. That image helps protect the word whole from doing too much work. The whole is not the field. The whole is the surprising lack of flags across part of the field. So when we begin with a missing crowd, we are beginning with the most honest version of the mystery. Something in the distribution is different here. Before we explain it, we have to prove that the difference is not just a trick of perspective. That proof requires distance. A galaxy that looks beside another galaxy may be millions or billions of light years in front of it or behind it. The sky compresses depth into a flat surface. The Boötes question only becomes serious when the flat surface opens into volume. Then the missing crowd is no longer a patch on a picture. It's a sparse region in cosmic space. Spend a little longer with a census because it keeps the whole story honest. The first evidence is not a mood about darkness. It's a comparison between the galaxies expected in a cosmic volume and the galaxies actually placed there by survey work. A shortage across such a region becomes meaningful only after many small measurements agree. That's why the map matters more than any single image. The pattern is built from accumulated positions. Boötes therefore begins as disciplined absence. The viewer can picture a giant auditorium with scattered seats filled, but the science asks for the seating chart, not the metaphor. Where are the galaxies? How far away are they? How does the count compare with nearby structure? Those questions make the mystery sturdier. They give the title a foundation before the script moves to distance and depth. And they protect us from the easiest mistake in the story. A dramatic word can make a map feel like a monster, but a census keeps asking the quieter question, what is actually counted here, and what is only being imagined because the count is surprising? A census also has a moral for the viewer. It teaches us to trust accumulation rather than spectacle. One galaxy missing from a catalogue means nothing. A whole volume with fewer galaxies than nearby volumes becomes a clue. The clue is stronger because it is modest. It does not ask us to imagine a cosmic object made of darkness. It asks us to notice that the universe, when counted carefully, has neighborhoods. Some neighborhoods are crowded beyond easy intuition, others are thin enough that their thinness becomes the defining fact. Boötes belongs to the second kind, so the missing crowd is the doorway, not the full answer. It gives us the observational reason to care before we bring in definitions, gravity, or simulations. One more reason to begin here. The missing crowd gives the viewer a clean way to separate observation from interpretation. The observation is the shortage. The interpretation asks why the shortage exists and how unusual it should be. If we confuse those two, the story becomes slippery. If we keep them separate, every later step has a foundation. So the first movement of the argument does not need a final theory. It needs a trustworthy emptiness, measured as a lack of expected galaxies across a large region. A careful census also asks what kind of galaxies are allowed into the count. Bright galaxies are easier to include. Faint galaxies can slip below a survey limit. A survey covering one slice of sky can miss structure just outside its edge. None of that makes the void imaginary. It tells us why every claim about its size has to travel with the method that produced it. Now imagine two address books for the same region. One lists only the largest buildings. The other includes small cottages, sheds, and isolated farms. The second book will contain more entries, but the district can still be sparse compared with downtown. Better coverage changes the detail. It does not automatically erase the contrast. That point matters for Boötes because famous numbers often outlive the survey choices behind them. A phrase like hundreds of millions of light years sounds like a clean object. The evidence behind it is more like a growing atlas. Researchers add redshifts and compare samples. They revise boundaries. Then they ask whether the broad, low-density feature survives. For the listener, this makes the discovery stronger. We are not leaning on one dramatic snapshot. We are watching an idea become testable. The void begins as a surprising shortage. Then it becomes a question about distance and sample depth. Density is where the argument tightens. So the redshift story gives us two gifts at once. It gives Boötes three-dimensional reality, and it gives us the humility to say what the map can support without pretending the map is perfect. One more piece belongs with the first map. The surrounding crowd is part of the measurement too. Boötes only becomes striking because other regions at comparable distances are richer. A shortage without a comparison is just an impression. A shortage beside walls and filaments becomes evidence. So the census has two jobs. It counts what is inside the sparse region, and it keeps track of what the nearby web looks like. The void is the difference between those counts at cosmic scale. That difference also explains why the story can last beyond a single famous number. Even if later surveys revise the boundary or add more galaxies, the central question remains, why does this part of the map sit so far below the crowd around it? That first comparison is also a safeguard against spectacle. We do not have to imagine a perfect circular gap. We only need the map to show a sustained fall in the usual galaxy crowd. Once the drop is measured across enough distance, the absence becomes part of the universe's geography. So the first chapter leaves us with a clean standard. If the crowd is truly missing in depth, then Boötes is not a visual trick. It is a real low-density place that needs a physical history. A galaxy on the sky gives us two easy pieces of information. We know where it appears left to right. We know where it appears up and down. But that is not enough to build a void. Now imagine looking at a city from far above with no street addresses. You can see lights, but you do not know which ones are nearby and which ones are far behind them. A dark patch might be a park. It might also be a place where distant lights are hidden by the flat view. Astronomers needed depth. For galaxies, one key tool is redshift. Light from a galaxy carries spectral lines, like fingerprints. As the universe expands, those lines shift toward longer, redder wavelength. The amount of shift helps estimate how far away the galaxy is in the expanding universe. But redshift is not magic. Galaxies have local motions. Surveys have selection rules. Faint galaxies are harder to measure. Still, Redshift turned galaxy maps from sky pictures into cosmic address books, and that is where the Boötes story entered modern large-scale mapping. In 1981, Robert Kirshner and his colleagues reported a remarkable void in the direction of Boötes. Their paper asked about a 1,000,000 cubic megaparsec void. Even the question mark mattered. The evidence was startling, and the map was still growing. The follow-up work in the 1980s deepened the case. More redshifts meant more addresses. More addresses meant the missing crowd could be tested, not just noticed. The absence was not a mood. It was a pattern in distant space. Think of dots lifting off a page. At first, the sky looks like a flat sheet of points. Then each point gets a depth coordinate. Some dots move forward, others slide far behind. The page becomes a volume, and in one part of that volume there are far fewer dots than expected. Here is why that mattered so much. A flat patch with few galaxies could be a projection effect. A three-dimensional volume with few galaxies is a structure problem. It asks how matter, gravity and time produced such a sparse region, but early maps were not final maps. They were bold steps into a universe that had not yet been surveyed with modern density. A region could look emptier before faint galaxies were added, before wider coverage arrived, before algorithms drew boundaries in different ways, so we should respect both sides of the history. The early Boötes reports were not silly exaggerations, they were serious signs from the data. At the same time, the first map of an absence is never the last word. Size can change, shape can change, contents can change as the survey improves. And this is the discipline that keeps the story honest. We do not need to turn the void into a legend. The real method is strong enough. Measure galaxies, place them in depth with redshifts, and ask whether a large volume is unexpectedly sparse. Now listen to how different that is from the popular image. The popular image says, something black sits out there. The scientific image says, the cosmic address book has an enormous region with very few entries. That difference matters for the rest of the documentary. A black object would need one explanation. A sparse volume needs another. It sends us into density and survey selection. Then it sends us deeper, into gravitational growth and the way galaxies trace a larger matter field. We can say the void was identified through mapping, not imagined through darkness. It became real because galaxies were assigned distances and the distribution remained thin. But once the map exists, the next question changes. We are no longer asking whether there is a scary black place. We are asking what cosmologists mean when they call a region a void at all. The word has to be cleaned before the science can move forward, and cleaning the word does not weaken the story. It lets us hear the real one. Once Boötes becomes a three-dimensional shortage rather than a black patch, every later claim has to answer to measurement instead of mood. The method also explains why discovery was a process, not a single magical night. Each measured galaxy was another address. Each address either filled the region a little or confirmed the scarcity. Science built the absence one coordinate at a time. That slow construction matters for trust. We are not asked to believe a dramatic illustration. We are asked to follow a chain of measurements from spectra to distance to density, and because the chain can be checked, it can also be revised. Better surveys do not ruin the story, they make the story more exact. The beauty of redshift is that it gives a distant galaxy a kind of postal code, not a perfect street address, but enough depth to separate foreground from background and turn a picture into a structure. Without that depth, a void would be easy to misunderstand. We might be looking between filaments. We might be seeing a survey limit. We might be fooled by the way a three-dimensional universe flattens onto the sky. With redshift, the question gets sharper. If the same direction remains sparse after distances are estimated, the shortage has weight. It occupies volume. The 1981 report matters because it arrived during a period when astronomers were learning that galaxy maps had much more texture than a smooth distribution. The universe was becoming a landscape of walls, clusters, and open regions. That historical moment gives Boötes a special role. It was not just one more oddity, it helped make the empty side of large-scale structure visible to the scientific imagination. But the question mark in the early paper is a good reminder. The first announcement of a void is not the same as a final atlas. The authors were dealing with limited data, real uncertainty, and a growing method that makes the story more trustworthy, not less. Science often begins with a startling pattern and then spends years asking how much of the pattern survives better measurements. For Boötes, the survival of the broad idea matters more than any single early number. The region stayed famous because the map kept pointing to a large underdensity, even as the details improved. Now imagine each redshift as a small depth pin pushed into a transparent model of the universe. One pin means little. Hundreds and thousands begin to show the skeleton. A sparse region is the place where the pins do not arrive in the expected numbers. That's why the next move is definition. Once the pins outline a sparse volume, we need to know what kind of structure the word void actually names. Stay with the redshift method because it is the bridge between suspicion and structure. A sparse direction on the sky could fool us. A sparse volume built from distances is harder to dismiss. The spectral shift gives each galaxy a rough place in the expanding universe. It lets astronomers sort foreground from background, and it turns a patch of sky into a layered map. That layering is why the 1981 and 1987 Boötes work belongs in the story. The void was not invented as a dramatic phrase. It emerged as researchers gave galaxies depth and noticed that one enormous region stayed thin. Better catalogues can refine that picture, but refinement is not failure. It's how a first startling clue becomes a durable scientific object. Redshift also gives the story its humility. The distance estimate is powerful, yet it comes through a chain of interpretation. Light leaves a galaxy. Expansion stretches it. Instruments record the spectrum. Astronomers compare the shifted lines. Each step is understandable, and each step can be improved. That's why the Boötes Void became a scientific object rather than a rumor about darkness. A rumor needs mystery to stay vague. A redshift survey invites correction. Better data can sharpen the shape, add interior galaxies, and refine the boundary without destroying the central fact of underdensity. That's the kind of mystery GNS can live inside. Not an uncheckable claim, but a map that becomes more interesting as the evidence improves. Depth also changes the emotional scale. A flat gap can be dismissed as a patch on a drawing. A volume with few addresses feels like a place in the universe. That place is still not a solid object, it's a statistical region. But a redshift gives it enough three-dimensional form for science to ask better questions. Once that happens, Boötes becomes more than a name. It becomes a test of how well our maps connect light, distance, and structure. A useful definition also separates galaxies from all matter. Galaxies are the lights we can count most easily, but the universe contains more than luminous islands. Dark matter shapes the gravitational landscape. Thin gas can be present without glowing like a galaxy. Small or faint systems can be missed by one survey and found by another. So a galaxy void is not always identical to a matter void. The two are related, but not interchangeable. Galaxies trace the web the way streetlights trace a city. Streetlights reveal roads and neighborhoods. They are not the pavement. They are not the people living there. Now bring that back to Boötes. When astronomers call it underdense, they are making a statement about the traces they can measure and the structure those traces imply. The careful version leaves room for hidden mass, faint galaxies, and improved maps. But care should not make the feature vanish in our minds. A rural region does not become urban because it contains roads. A low-density cosmic region does not become average because it contains some galaxies. The difference is measured against the larger pattern, and this is where the word underdense becomes emotionally useful. It lets us keep the awe without pretending to know something false. Boötes is not a perfect emptiness. It's a huge departure from the expected crowd, and that departure is enough to demand an explanation. The redshift map also carries a quiet warning about distance. Redshift is tied to cosmic expansion, but galaxies can have their own motions inside the web. Clusters, walls, and flows can blur the clean relationship between redshift and position. Astronomers know this. They do not treat every redshift as a flawless ruler. They use it as a powerful coordinate with known limits, then compare many galaxies so individual motions do not decide the whole pattern. For Boötes, that means the void is not built on one distance estimate. It's built from a population. The more galaxies placed in depth, the more the sparse volume can be tested. And because the method is population-based, the mystery stays scientific. A better distance model can adjust the map. It cannot be replaced by a mood about darkness. Redshift surveys made Boötes serious because they turned absence into a volume with coordinates. Each added galaxy could have weakened the claim or refined it. Either outcome would have been useful. The point was never to protect a legend. The point was to test a sparse region until its real shape became clearer. The most important correction is simple. A cosmic void is not absolute nothing. It's a region with less matter and fewer galaxies than the cosmic average. Now picture a rural valley compared with a downtown core. The valley may have roads and farms. A few cabins may sit inside it, but compared with the city, it is still underdense. But compared with the city, it is sparse. Calling it rural does not mean nobody lives there. It means the density has changed. The Boötes Void works the same way. It can contain galaxies and still be a void. It can contain gas and dark matter and still be dramatically underdense. The term is not a claim that the universe has been erased there, but this correction often feels disappointing for only a second. Then it becomes more interesting, because a nearly empty region with a few galaxies inside is not a failed mystery, it's a better measurement. And those few objects matter. They tell us the void is not a perfect blank. They give astronomers probes inside the sparse environment. They turn the void from a word into a place with evidence scattered through it. So the question is not, why is there nothing there? The better question is, why is the density so low compared with the regions around it? That shift changes everything. Here is another way to hear it. Weather maps show pressure systems with soft contours. Nobody thinks a high-pressure region has a glass wall around it. The boundary is an interpreted line drawn through a changing field. Cosmic voids have that same kind of softness. A void finder can use one galaxy sample and draw one shape. A deeper survey can use fainter galaxies and refine the interior. Another method can split a complex region into smaller connected basins. The void remains meaningful, but the boundary is not a solid surface. So the phrase 300 million light-years must be handled carefully. It gives the listener scale. It does not give a perfect ruler measurement from one polished edge to another. Now think about how easily the misconception spreads. If a void contains galaxies, someone might say the void is debunked. But that misunderstands the claim. A desert with towns in it remains a desert compared with a rainforest or a metropolis, and Boötes is powerful precisely because it forces that distinction. It's not the absence of everything, it's the absence of the expected crowd. The science lives in that comparison. We should also remember that galaxies are only tracers. They are bright, useful tracers of structure, but they do not show every bit of matter. Dark matter, diffuse gas, and faint objects can exist where the obvious galaxy count is low. So when we say the void is underdense, we are not saying reality failed there. We are saying the matter distribution and galaxy distribution fall below the average in a coherent, mapped region, but there is still weight in the word void. It tells us the universe does not smooth itself into a gentle fog. It develops contrast, with some places becoming crowded while others become sparse. The sparse places are not mistakes, they are part of the pattern. Once that definition is clean, Boötes stops being a spooky object and becomes a doorway into the largest architecture we know. The web has bright strands. It also has an empty side. This definition also protects the listener from a false disappointment. The discovery of galaxies inside a void is not a gotcha. It's what a careful definition allows from the beginning. We can hold both facts together. The region contains things. The region contains far fewer things than a comparable part of the cosmic web. Both statements are necessary. That balance is the difference between a mystery channel and a science documentary. We keep the strange fact, but we remove the misleading picture. The word underdense may sound less dramatic than empty, but it is much more useful. It gives us a comparison. It says this region is being judged against the average density of matter and galaxies in the wider universe. That comparison is what lets us be precise. If a place has 1 galaxy or 10 galaxies, the question is not settled. Even many faint galaxies do not end the comparison. We still ask how that population compares with a similar volume elsewhere. And because survey samples differ, precision also demands humility. A map of bright galaxies can make a region look one way. A deeper map that includes fainter galaxies can reveal more internal detail. But deeper detail does not automatically erase the structure. Adding roads to a map of a desert does not turn the desert into a city. It gives you a better map of a sparse place. Boötes should be heard in that same way. The internal galaxies are not exceptions smuggled into a false claim. They are part of the claim when the claim is stated correctly. Now think about density in ordinary life. A room can feel crowded at a party and empty the next morning, even though furniture remains in it. Density is about how much occupies a space compared with expectation. Cosmology uses more exact tools, but the intuition is similar. The void is not a magic word for nothing. It's a way of describing a low-density region in a universe where density varies. This also explains why boundaries are soft. If density rises gradually from the center towards surrounding walls, no single natural fence appears. Researchers choose useful thresholds to describe the pattern. Nothing about that is weakness. It's how many real natural systems work. Storms have fuzzy edges, so do forests. A boundary can be gradual and still be meaningful. So Boötes remains real in the way a vast low-pressure system is real. It's a mapped pattern in a field, not a carved object floating in space. The definition deserves extra space because it rescues the topic from 2 bad endings. One bad ending says the void is absolute nothing. The other says any galaxy inside makes the void fake. Underdensity avoids both mistakes. It lets a region contain objects while remaining sparse compared with the cosmic average. It also lets boundaries be gradual instead of pretending there must be a hard rim. Nature behaves more like that on large scales. Fields change, densities rise and fall. Researchers draw useful contours across those changes, so Boötes is not weakened by a careful definition. It becomes a better object of study, measurable, imperfect, and real. The definition also changes how we hear the silence of the region. Silence in a concert hall is not the absence of air. The seats are still there. The walls are still there. What is missing is the expected sound. It's the absence of expected sound. It has meaning only against the performance around it. A cosmic void is similar in spirit. The low density has meaning because the universe around it is not equally low everywhere. And that is why the word average matters. Without an average, sparse has no target. With an average, Boötes becomes a measurable departure from the surrounding cosmic pattern. And once it is measurable, it can be tested, it can be compared, it can become useful evidence. Underdensity is also a more generous word. It leaves room for complexity. It allows a sparse interior and gradual edges. It also leaves room for different traces as surveys improve. A literal hole cannot do that. A literal hole demands a clean shape and a perfect absence. The universe rarely gives us such simple objects on these scales. The Boötes Void is richer because the better word is less theatrical. Large-scale maps also teach a subtle lesson about names. We name clusters because galaxies crowd there. We name walls because galaxies line up in sheets. We name filaments because strings of galaxies stretch across enormous distances. Voids deserve the same seriousness because the low-density regions complete the geometry. Look at a spider web after rain. The droplets make the strands bright, but the openings tell you the web's true pattern. If you only counted droplets, you would still infer the spaces between them. The cosmic web works through a similar logic, with galaxies as luminous marks on a much larger arrangement. Boötes is one of the openings large enough to become memorable. Its fame can make it sound isolated, as if the universe has one strange empty room. The better picture is a whole building of rooms and corridors, with Boötes as one unusually large chamber that made astronomers pay attention. That framing protects the mystery from collapsing into trivia. We do not have to say Boötes is unique to care about it. A famous canyon can belong to ordinary geology and still reveal the force of erosion better than a smaller cut in the rock. In the same way, Boötes can belong to the cosmic web and still be the feature that helps us understand the web's negative shape. It's the absence that makes the architecture visible. The definition also affects how we imagine scale. A void can be large because its low-density basin is broad, not because every point inside has the same emptiness. The center may be especially sparse. The outer parts may rise gradually toward denser structure. Now picture a valley again, but from above. The deepest floor is not the whole valley. The slopes matter too. A boundary drawn around the valley depends on where you decide the slope has become ordinary ground. Boötes can be handled the same way. Its fame comes from the whole low-density region, while its details depend on which traces and thresholds define the basin. That gives the listener a sturdier mental image, not a bubble, but a broad depression in the galaxy field. A clean definition also keeps language calm. We can call Boötes sparse, low density, mapped, and extreme without calling it impossible. That precision does not drain the wonder. It lets the listener stay curious while the science stays honest. When we picture structure, we usually picture what is present: stars, galaxies, and clusters. We imagine bright knots and long filaments crossing the dark. But a web is not only its threads. The open spaces help define the pattern. Remove the gaps from a net, and the net disappears too. Now place Boötes inside that thought. The void is not outside the cosmic web. It's one of the ways the web is organized. It sits among the crowded regions as a low-density chamber inside the same large pattern. Astronomers call this large-scale structure. On the biggest maps, galaxies do not spread evenly. They gather into clusters, wars, and filaments. Between those features lie voids, the broad regions where the galaxy density falls. And here is the turn that makes the subject beautiful without making it vague. The bright parts and the sparse parts grew together. Filaments are not decorations placed on top of emptiness. Voids are not accidental holes between finished structures. They are related outcomes of the same cosmic history. Think of stained glass. The bright pieces draw your eye, but the dark lines and empty spaces tell you where one shape ends and another begins. Or think of a fishing net pulled through water. The strands matter, the openings matter too. Boötes gives us an especially memorable opening in that net. It's a place where the emptier side becomes large enough for the viewer to notice. The scale makes the negative part of the architecture impossible to ignore, but we should not drift into generic void facts. Boötes remains our anchor because it asks the question in a cold viewer way. How can a famous part of a galaxy map be defined mostly by what is missing? The answer begins with contrast. A wall of galaxies is dense because matter collected there. A void is sparse because, over time, matter did not remain there in the same way. Each side makes the other readable. Now imagine flying through a digital map. You pass a filament, then a cluster, then a wall. Galaxies appear like beads on invisible strings until the beads thin and the space opens. You have not left the universe, you have entered another part of its structure. Pure black visuals can mislead for exactly this reason. A dark starfield says almost nothing. A map with crowded boundaries and a sparse interior says a great deal. It shows the relationship between presence and absence, and that relationship is the reason voids are useful to science. They help trace how matter is distributed. They reveal where galaxies avoid the average. They test whether our picture of structure formation grows both the crowded and the quiet places correctly. So Boötes is not a hole punched through a finished universe. It's a region inside a universe that never became smooth. The largest maps are lumpy, braided, and uneven. Here is the listener-friendly version. The cosmic web has bright strands and dark rooms. The rooms are not outside the building, they are part of the design. But the web did not begin already drawn. Something had to make matter gather in one place and leave another place thin. To understand why the gap exists, we have to watch gravity build it. A map of only clusters would miss the pattern. A map of only voids would also miss it. The real universe is the relationship between them. Boötes is useful because it makes that relationship hard to ignore. It gives the empty side a name. It turns a background feature into the main evidence. And once absence has a name, we can ask how it formed instead of merely staring at it. The cosmic web is easy to oversimplify because the word web makes us imagine only the strands. But the largest pattern is just as much about the spaces between those strands. If galaxies lived everywhere with equal density, the universe would have no web. It would have a fog. The web appears because matter is unevenly arranged. Boötes is one of the places where that unevenness becomes a central character. It teaches us that absence can be organized enough to map. Now picture a nighttime satellite view of Earth. Bright cities trace coasts, rivers and roads. Dark regions between them are not outside geography. They can be forests, oceans or mountains. The planet has structure because it has differences, and the darkness belongs to the map. Cosmic voids are not Earth landscapes, of course, but the analogy helps. The lack of lights is information when you know what the lights trace. Galaxies trace the cosmic web imperfectly, yet powerfully. When their distribution leaves a large open region, that opening tells us something about the underlying structure. Boötes should not become generic emptiness for exactly this reason. Its value is relational. It matters because of the walls and filaments around it, and because of the wider web it helps reveal. The underdense region is like a pause in music. A pause is not a broken note. It shapes the phrase. It gives the surrounding sound its form. So the web's empty side is not decorative. It's part of the architecture. It helps show where matter has gathered and where the cosmic flow left a lower density chamber. Once we see that, the next question becomes physical. What process turns tiny early differences into bright strands and vast sparse rooms? The web image helps because it keeps relationship at the center. A filament is meaningful partly because nearby regions are not equally dense. A void is meaningful because the surrounding cosmic web is richer. If we watched only the bright places, we would miss half the architecture. The low-density chambers tell us where matter did not collect with the same strength. Boötes gives that chamber a memorable name. It lets the viewer understand that the universe's largest pattern includes spaces as well as strands. So emptiness here is not wallpaper. It's structural information. Here the phrase large-scale structure earns its name. The structure is not one object, it's the arrangement of many objects across vast distances. Boötes participates in that arrangement by being sparse. Its role is not to shine, its role is to outline the brighter web by contrast. That may be the deepest correction in the whole video. The universe is not only built where things are, it's also built through the relationships between crowded regions and quiet ones. The empty side is therefore not a gap in the story, it's one of the story's main shapes. The web frame also helps with memory. The listener can carry one image forward. Bright strands around darker chambers, every later detail can attach to that image. Redshifts place the strands in depth. Gravity grows them. Simulations compare them. Void galaxies light a few points inside the chamber. That single mental map keeps the documentary from becoming a list of facts. Gravity does not need a dramatic shove to begin this process. A tiny initial difference is enough if the universe gives it time. Slightly denser places pull a little more strongly. Nearby matter responds. The advantage grows. Over billions of years, the small imbalance becomes a real landscape. Picture rain falling on a field with barely visible slopes. At first, the surface looks almost flat. Then water begins to find shallow channels, and those channels deepen because more water follows them. Higher patches drain away, while lower paths become streams. The final pattern looks far more dramatic than the first difference. Cosmic structure formation is not the same as rainfall, but the intuition helps. Early density ripples were small. Gravity amplified them. Matter moved toward knots and ridges. Galaxies formed more easily where matter collected. Regions that began slightly underfilled became poorer relative to the average. Boötes asks us to apply that chain on a scale that strains intuition. The sparse region is not carved out after the fact. It's part of a long competition between crowded places and quiet places as the web grows. Dark matter makes the picture deeper. Most matter does not shine, yet it helps guide where ordinary matter falls. Galaxies are bright witnesses to a darker scaffolding. A void in the galaxy map therefore points toward a broader gravitational history, not just a missing set of stars. The web picture also helps us avoid a common mistake. Voids are not simply the leftovers after galaxies have been placed. They are part of the same distribution. A filament has meaning because nearby matter is less dense. A void has meaning because nearby matter is more dense. Now imagine drawing a map with only borders and no countries, or only countries and no borders. Neither version carries the full information. The web needs both sides of the contrast. Boötes sits in that contrast. It's not a blank beyond the map. It's a mapped, low-density region whose importance depends on the surrounding high-density features. So when we say the web has an empty side, we are not adding poetry. We are naming a structural fact. Large-scale organization includes where galaxies are scarce. Seen this way, a void is not the opposite of structure. It's structure expressed through low density. Boötes matters because it makes that expression large enough for us to follow by ear. We can track the map, we can test the contrast, then we can ask for the mechanism. The early universe was not perfectly smooth. It was close, but not exact. Tiny density differences were already present, like faint wrinkles in an otherwise even field. Now give those wrinkles time. Gravity pulls matter toward places that are already a little denser. A small advantage becomes a larger advantage. A slight crowd becomes a stronger pull. Over billions of years, the differences grow. Here is the heart of structure formation. Dense regions become denser. Matter collects into halos and galaxies. Groups gather. Clusters and filaments grow into the brightest skeleton of the web. Underdense regions become emptier compared with the average, because matter is more likely to flow toward the growing crowded places. But be careful with the mental picture. Gravity is not a vacuum cleaner parked at the edge of Boötes, sucking everything out. The better image is a shallow landscape after rain. Water gathers into the lower channels. The raised areas become drier by comparison. And in the cosmic version, dark matter is crucial. It provides much of the gravitational scaffolding. Galaxies form inside dark matter structures, so the galaxies we see trace the scaffolding imperfectly. They are bright traces, not the whole field. Here is what that means for a void. If a region begins slightly underdense, it has less gravitational pull than the denser neighborhoods around it. Matter tends to join the growing walls and filaments. The underdense region expands relative to those structures and becomes more pronounced. The result is not a manufactured emptiness. It's a natural contrast created by growth. The same physics that builds a cluster also helps define the void beside it. Now bring Boötes back into view. Its emptiness is not a separate problem from the galaxies around it. The surrounding cosmic web is part of the explanation. The crowded structures and the sparse interior belong to one connected history. This also protects us from a common overclaim. A huge void does not automatically mean something broke. Voids are expected if small early differences grow through gravity. The question is whether a particular void is larger emptier or more common than the model predicts. And that is a different kind of tension. The question is not, how can emptiness exist? The question is, how extreme can this form of emptiness become under known cosmic growth? Think about a crowd leaving a large hall through several exits. People do not vanish, they drift toward paths of motion. Corners and open floor areas become sparse because the movement is organized elsewhere. The empty areas tell you about the flow. Boötes tells us about cosmic flow in that broad sense. It marks a region where the matter that became visible galaxies did not collect as strongly as it did in the nearby web. We should not pretend that every detail is settled. Simulations, survey maps, and galaxy samples must still be compared. The inside of a void can hold substructure. Boundaries can depend on the method, but the basic mechanism is not mystical. So when someone asks why the whole exists, one answer is, because gravity amplifies difference. The universe did not simply fill every volume with the same number of galaxies. It let tiny early variations grow into a landscape. The next question is scale. If gravity can build gaps, why did this one become famous for being so large? That takes us back to the number in the title. The phrase relative to the average does a lot of work here. A void becomes emptier compared with the mean as the crowded regions win more matter. The universe is building contrast, not deleting space. We can picture the process without making it cartoonish. The low-density region is not being scraped clean. It's losing the competition for matter to places that began with a slight gravitational advantage. Voids and filaments become twins in the story for this reason. One grows brighter because the other stays sparse. Gravity is usually introduced as the force that pulls things together. That's true, but in a lumpy universe it also creates contrast. Pulling matter toward one region leaves another region poorer by comparison. The void is born from that comparison. It's not carved out afterward. It grows as the dense places win more matter over time. The early universe matters for this reason. The first density variations were tiny, but they gave gravity something to amplify. A region slightly denser than average could become a future gathering place. A region slightly underdense could become a future void. Now imagine a sheet with shallow dips and rises. Roll many marbles across it for a long time. The marbles collect in the dips. The higher areas lose them. The emptier areas are not mysterious holes. They are consequences of the same landscape. In the universe, that landscape is not a rubber sheet in space. It's the gravitational pattern produced by matter, especially dark matter. Galaxies form within that pattern and light up parts of it. Boötes asks us to follow the darker part of the pattern. The visible galaxies are sparse because the underlying history did not favor normal crowding there. And over billions of years, even small differences can become enormous. That's the quiet power of cosmic time. It turns slight irregularities into structures hundreds of millions of light years across. But the process is statistical, not handcrafted. We should not imagine one special event creating Boötes unless evidence points there. The broad explanation is the growth of structure from initial unevenness. That explanation can still leave details open. How exactly should a void this large be counted? Is it one region or a connected complex? How does its profile compare with simulations? Those are strong questions because the mechanism is strong. Once gravity can build gaps, scale becomes the next pressure point. The mechanism needs room because it changes absence from a puzzle into a consequence. Gravity gathers matter toward denser regions. Over time, that gathering increases contrast. A slightly underdense region does not have to be scraped clean. It simply loses the competition for matter compared with its denser neighbors. The walls and filaments grow richer, while the low-density region stays sparse. Boötes can be understood through that patient process. It's not a sudden scar. It's the large-scale result of small early differences amplified across cosmic history. The explanation is calmer, but it carries enormous weight. The mechanism has a patient violence to it, though not a frightening one. Gravity never needs to hurry. It has billions of years. It works with tiny advantages until those advantages become architecture. A little extra density becomes a stronger gathering place. A little less density becomes a region that cannot compete as well. The difference widens. That widening is what makes voids feel strange. They are not made by a dramatic explosion. They are made by ordinary physics given extraordinary time. Boötes is therefore a lesson in patience. The universe can build enormous contrast without a single theatrical event. This mechanism is why voids are not failures of cosmic construction. They are products of it. A universe that grows filaments must also grow the spaces between filaments. A universe that makes clusters must also leave lower density regions outside those clusters. Boötes is the large-scale version of that simple truth. The gap and the gathering belong together. Scale language works best when it is honest about what is being scaled. The phrase 300 million light-years gives us the right emotional weight. It says Boötes is not a gap between neighboring galaxies. It spans a distance so large that light itself needs hundreds of millions of years to cross the order of magnitude. But a void is not a marble with a diameter. Researchers may describe an effective size or a longest span. They may use volume too. Each choice comes from a boundary decision. Those choices can all be useful, and they do not have to produce identical numbers. Imagine measuring a cloud. One person measures the brightest core. Another includes the faint outer haze. Another asks how much sky the cloud covers above a certain brightness. Nobody is lying. They are answering related but different questions. Boötes has the same problem in cosmic form. Its edges are density transitions. Its interior may contain subregions with different sparseness. Nearby structures can make the outline look connected in one analysis and more broken in another, so the number should land as scale, not as a promise of a polished edge. The void is enormous. The exact phrasing depends on map, method, and definition. That combination is not a weakness in the story. It's one of the reasons the story belongs to science rather than mythology. The growth story also explains why voids tend to become rounder and emptier in a loose sense, while the crowded regions become more tangled. Matter streaming away from low-density regions does not make a clean vacuum. It deepens the contrast between the basin and the walls around it. So Boötes should not be pictured as matter being sucked out by a hidden machine. The better image is slower. A low-density region expands relative to its surroundings, while matter preferentially joins the web outside it. Over cosmic time, the difference compounds. The rich get richer in structure. The sparse become sparser compared with the average. Enough to make an enormous underdensity feel less impossible. It's not produced in one event. It's the long result of small initial differences amplified by gravity and expansion. The same process also means voids are old stories. They carry memory from early conditions and from billions of years of gravitational growth. Boötes is not a recent accident in the universe. It's a mature feature in a very old pattern. We need to keep that difference clear. "300 million light-years is an enormous phrase. It feels precise because the number is round and cinematic. But the real science behind it is more subtle. Now imagine measuring a coastline. At one map scale, the coastline has one length. Zoom in, and every inlet and bend adds detail. The number changes because the boundary was never a perfect geometric edge. A cosmic void has the same kind of problem. Its size depends on the boundary we choose. It depends on which galaxies enter the sample. It also depends on whether connected underdense pockets are merged into one complex region or separated into smaller basins. That does not make the number useless. It gives us a sense of scale. Boötes is not a small gap. Popular descriptions often place it in the range of hundreds of millions of light-years across, with roughly 300 million used as the clean viewer-facing hook. But we should hear the word roughly. A void is not a metal sphere whose diameter can be measured from polished rim to polished rim. It's a region in a distribution, and distributions have thresholds. Here is the important listening distinction. The number tells us this is a vast underdense region. It does not tell us that a hard-edged ball of emptiness floats in space. Survey depth matters too. Early searches saw bright galaxies above certain limits. Later work can add fainter galaxies or cover different volumes. As the catalogue changes, the interior population and the apparent boundary can change as well. And redshift distances carry assumptions. On the largest scales, the expansion of the universe gives us a distance framework, but local motions and cosmological parameters still matter. The map is powerful. It's not a perfect ruler handed down from the sky. Now think of fog over hills. From far away, one valley looks like one smooth basin. As the fog lifts, smaller ridges and pockets appear. A giant void may sometimes be better understood as a connected complex of underdense regions, rather than a single flawless sphere. That possibility does not erase Boötes. It makes it more scientific. A real structure can have internal shape. A famous void can be both memorable to the public and complicated to define in research. Honest language matters here. We can say roughly 300 million light-years to communicate scale. We should not say the universe has a clean circular hole exactly that wide. But there is another reason the number matters. Scale affects expectation. The larger the underdense region, the more carefully we ask what produced it. Normal structure formation may be enough. Surveys may have missed populations, or the region may sit at the extreme tail of known voids. Here is a useful analogy. A dry patch in a garden is not surprising. A dry plain stretching to the horizon makes you ask about weather and soil. Drainage matters too. History is the deeper question behind the landscape. Size does not automatically mean impossibility. It means the explanation has to carry more weight. Boötes became famous because its scale made the shortage legible. A small sparse pocket might vanish into ordinary map texture. A vast sparse volume becomes a landmark, so the title number is a doorway. It lets us feel the scale before the caveats arrive. Then the science improves the picture by showing why scale, boundary, and definition must be handled together. A fuzzy boundary does not make the void fake. It makes the few galaxies inside it even more important. For a viewer, the number is still valuable. It puts the mind on the right scale. We are talking about a feature far larger than a galaxy, larger than a group, larger than the local structures we usually imagine. For a scientist, the number has to be attached to a method. What sample defines it? What threshold marks the edge? What cosmology turns redshift into distance? Those questions keep the claim from hardening into a myth. The best version of the title survives that honesty. It says, "This is huge." The script adds, "And huge does not mean simple." Numbers are powerful in a title because they give the mind something to hold. 300 million light-years says, do not imagine a small dark patch. Imagine a feature on the scale of the cosmic web itself, but a number can also pretend to be cleaner than the object it describes. That's why we need to separate scale language from false precision. A void boundary comes from density. Density changes gradually. The center may be sparse, the edges less sparse, the surrounding web richer. Choosing where the void ends depends on a definition. Different surveys can also weight the map differently. Bright galaxies and faint galaxies do not trace structure in exactly the same way. Red and blue samples can differ too. The tracer changes the map, so the measurement is not like measuring the width of a door. It's more like measuring the width of a weather system. The system is real. The edge depends on the contour you choose. Boötes survives that complexity because the scale remains huge under reasonable descriptions. The caution does not erase the landmark. It prevents us from imagining a hard circular tunnel. Now listen to what the number does honestly. It tells us that the underdensity is large enough to require cosmic explanation. Local accidents cannot easily carry the story. A small gap between neighboring galaxy groups might be ordinary texture. A famous void, hundreds of millions of light-years across, pushes us toward large-scale structure, survey history, and simulation comparison. Over works best this way. The number makes us look harder. It does not give us permission to overclaim. And once the number is honest, the interior becomes more interesting. A huge, sparse region with a few galaxies inside is a better scientific object than a perfect blank ever could be. The scale discussion must hold awe and caution together. Hundreds of millions of light years is a real invitation to wonder. It tells us the feature is large enough to belong to the cosmic web, not to ordinary local texture. But the same scale cannot be treated like a metal diameter. A void edge depends on density thresholds, galaxy samples, and the survey used to trace the region, so the number should be heard as honest scale language. It points to a vast underdensity while leaving room for soft boundaries and revised maps. That honesty makes the title stronger, not weaker. Scale also affects imagination. A human mind can picture a valley, a country, perhaps even a galaxy with effort. Hundreds of millions of light years push beyond ordinary comparison. So the script has to do two things at once. It must let the number feel enormous, and it must keep the number from pretending to be a hard edge. Approximations are not a weakness here. They are a sign of honesty about the object being described. A void scale is real enough to matter and soft enough to require definition. Boötes lives in that tension, so we can let the title keep its force while teaching the viewer how to hear it. 300 million light years means enormous, not exact. Whole means underdensity, not rupture. Those translations are not evasions. They are the route from clickable language to accurate understanding. And once translated, the title becomes better. It points to a real scientific problem rather than a false cosmic wound. Those interior galaxies also change the emotional shape of the story. Without them, Boötes could become an empty stage where nothing happens. With them, it becomes a sparse laboratory. The few lights inside let us ask how galaxies grow when the neighborhood is quiet. A galaxy in a dense cluster lives a crowded life. It can feel tides from neighbors. It can lose gas. It can merge, be disturbed, or have its star formation shaped by the environment around it. A galaxy in a void lives with fewer close companions. Its history can preserve different clues. Now we have to be cautious. Not every void galaxy behaves the same way. Samples differ. Selection matters. Some studies find trends toward bluer, gas-rich systems in low-density environments. Star formation can look different there too. But any single property depends on how the comparison is built. The safe lesson is still rich. The galaxies inside and around voids help astronomers separate nature from neighborhood. They show how environment changes the odds of certain galactic histories. Boötes, therefore, does not lose its meaning when we find galaxies inside it. The interior galaxies make the underdensity more useful. They are like field stations in a sparse landscape, places where the emptiness can be studied from within rather than only from the rim. The measurement problem also has a listening benefit. It lets us treat the title number as honest scale rather than a trap. The viewer clicked because 300 million light years sounds impossibly large. The script can honor that feeling while explaining why nature does not supply a crisp measuring tape. A soft measurement is not a weak measurement. Coastlines require definitions. Storms and forests do too. Galaxy voids are no different. The shape depends on the contour chosen, but the phenomenon remains real. For Boötes, the most important statement is not a false precision down to the edge. It's the order of magnitude, a vast cosmic underdensity, large enough to become one of the iconic examples of void structure. That statement is strong, clear, and safer than pretending the void has a polished rim. The number, therefore, works best as a promise of scale. It tells us the question is large enough to matter. Then the documentary earns that scale by explaining why the boundary is interpreted rather than seen. The most useful correction to the Boötes myth may be the simplest one. Now there are galaxies inside cosmic voids. Now pause on that without losing the main point. The existence of galaxies inside Boötes does not cancel the void. He tells us what kind of void we are dealing with, underdense, not empty. Picture a few cabins spread across a wide valley. If you expected a city and found only isolated homes, the valley still counts as sparse. In fact, the cabins help you understand the place. They show where roads might be, how far apart people live, and what the environment allows. Void galaxies do something similar. They give astronomers test particles inside low-density regions. They help us ask how galaxy formation changes when the usual crowded environment is missing. In dense regions, galaxies interact more often. They can tug on each other or merge. Gas can be stripped. Cluster environments can shape their growth. In a void, a galaxy may live a more isolated history. That isolation becomes a laboratory, but we need careful wording. Void galaxies are not alien, impossible, or trapped. They are ordinary galaxies in an unusual neighborhood. Some studies find that void galaxies can differ from galaxies in denser regions, but the exact claims depend on the sample and method. Here is the safe idea. Low-density environments affect the story of galaxy growth. They change the neighborhood. They change the opportunities for interaction. They make the few galaxies inside voids scientifically useful, rather than embarrassing to the definition. And for Boötes, that is crucial. If the void were treated as absolute nothing, every internal galaxy would look like a contradiction. Once we understand underdensity, each internal galaxy becomes evidence. Now think about a field biologist crossing a sparse ecosystem. The point is not that life cannot exist there. The point is that life exists under different conditions. The sparse environment is part of the data. The same discipline applies here. A void galaxy helps locate the interior. It helps test the map. It lets astronomers compare galaxies in sparse regions with galaxies in walls and filaments. This also changes the emotional feel of the story. The void is not a dead zone. It's not a cosmic blank where reality disappears. It's a low-density environment with a few bright witnesses. We can use those witnesses to separate myth from measurement. A myth wants perfect emptiness. Measurement gives us a more interesting truth, a vast region where galaxies are rare enough to define a structure, yet present enough to study. But there is a trap here. We should not overcorrect and say, because galaxies exist inside it, Boötes is ordinary. A sparse region can contain objects and still be extreme. A desert can have towns and still be a desert. So the galaxies inside do two jobs at once. They prevent literal whole language, and they make the underdensity more concrete. They show that the void is a measurable environment, not a slogan. Now we have a better question. If Boötes is not alone in containing sparse galaxies, how does it compare with the wider population of cosmic voids? To answer that, we have to zoom out from one famous absence. The few galaxies also give the listener a way back into the void. Absolute emptiness is hard to think about. A sparse environment with isolated points can be pictured, mapped, and compared. Those points make the scale more human. They are like lamps across a huge plain. The darkness between them tells us the plain is wide, but the lamps prove the place can still be studied. So the interior population is not a footnote. It's one of the strongest protections against the wrong mental image. Interior galaxies are like lanterns in the sparse room. They do not fill the room, but they help reveal its size and character. They also tell us about its environment. If we remove them from the story, the void becomes a cartoon. If we treat them as proof the void is fake, we make the opposite mistake. The right move is to let them do their scientific work. Those galaxies help connect the void to galaxy formation. A galaxy growing far from dense clusters may have a different interaction history than one living in a crowded wall. It may avoid frequent mergers. It may keep or use gas differently. It may have a quieter neighborhood. The exact properties need careful sources, but the environmental question is real. Boötes therefore gives us two scales at once. On the large scale, it is a mapped underdensity. On the smaller scale, the few galaxies inside are individual laboratories. Now picture a long road across a sparse plain. A few houses along the road do not make a city, but they let you ask how people live where neighbors are rare. Void galaxies play that role in cosmic form. They show what galaxy growth can look like where the large-scale environment is thin. So the phrase completely empty should not survive past the opening correction. It blocks the better question. The better question is how low-density environments shape the objects that do exist there, and for the viewer, this is a satisfying turn. The void is not less real because it contains galaxies. It's more knowable. The few bright objects inside Boötes give the vast absence handles. They let us move from myth to map, from map to environment, and from environment to comparison. Interior galaxies give the listener handles inside the sparse region. They show that Boötes is not a featureless blank, and they help reveal what low-density environments are like. A galaxy in a void has a different neighborhood from a galaxy in a crowded cluster. That difference can matter for interactions and growth. Environment matters too, even when exact properties depend on the survey. The few galaxies inside therefore serve two roles. They correct the literal whole image, and they let scientists study the void from within. They are not contradictions, they are witnesses. Interior galaxies also create a useful emotional turn. The void is not hostile to knowledge. It gives us fewer visible points, but the points it gives are precious. Each one can be studied for its light and distance. Its color matters too. Then we ask how it sits inside the wider sparse region. That makes the void less like a locked room and more like a quiet field station. There's not much there, but what is there matters more because the neighborhood is so unusual. For the viewer, that is a better image than pure absence. It gives emptiness texture without denying the underdensity. The internal galaxies also remind us that the void has history. They formed, evolved, and shone inside a low-density environment. Their presence means the region can be sampled from within. They are not decorations in the story, they are probes. A few probes across a vast space are exactly what make the scale feel real. Modern void catalogues widen the lens without taking Boötes away from us. Surveys such as Sloan-style galaxy maps reveal many underdense regions across large volumes. Algorithms can search for empty spheres, watershed basins, or connected low-density zones. Each method has its own strengths, but catalogue abundance does not make every void interchangeable. Some are small, some are stretched, some are nested inside larger complexes. Some lie near dense walls that make the contrast especially striking. Boötes remains memorable because the early map made its scale and sparseness so hard to ignore. Think of lakes on a continent. Finding thousands of lakes does not make the largest or strangest lake boring. It gives us a population for comparison. We can ask which features are typical, which are extreme, and which depend on how shorelines are drawn. Boötes plays that role in the larger family. It helps the viewer care about one named feature while the science compares that feature with a broader statistical landscape. So the honest phrase is extreme, not alone. Alone would be too dramatic. Ordinary would be too flat. Extreme lets the mystery survive in the right place, not in supernatural emptiness, but in how far a known kind of structure can go. Interior galaxies can also reveal the timing of growth. In dense regions, galaxies interact often enough that their histories can become tangled. Mergers, gas stripping, and cluster environments can rewrite their visible features. In sparse regions, fewer encounters can let other processes stand out. Gas supply and slow star formation may matter differently. Isolation may matter too. The point is not one simple cause. The void becomes a natural contrast experiment. We should not overstate the results. A void galaxy is still a galaxy, governed by ordinary physics. But the setting changes the odds. The few galaxies inside Boötes are not footnotes. They are part of the evidence that lets astronomers ask what environment does to galaxy formation when the environment is unusually quiet. A sparse laboratory is valuable precisely because it is quiet. Fewer neighbors mean fewer environmental complications. The galaxies do not become simple, but some influences become easier to separate from the crowd. Boötes is famous, but it is not the only void. Modern surveys reveal many underdense regions across the large-scale map of the universe. Now imagine a landscape full of lakes. One lake can be unusually large, historically famous, and visually memorable, but it still belongs to a class of features produced by the same geology and climate. Cosmic voids work in a similar way. Surveys such as those built from Sloan Digital Sky Survey data and related galaxy catalogues identify void populations. Different void finders use different methods, but the broad result is clear. Underdense regions are common parts of large-scale structure. That helps us place Boötes. It's not a lonely, impossible object. It's an extreme and memorable member of a known family. But we should not flatten it into nothing special. Historically, Boötes mattered because it made large-scale absence difficult to ignore. The apparent size and scarcity were striking. It became one of the voids people remembered because it gave absence a name and location. Here is the balance we need. Expected does not mean boring. Extreme does not mean impossible. Boötes can sit in the tail of a distribution and still be part of the same cosmic web story. Think of a canyon. The fact that canyons exist does not make a Grand Canyon uninteresting. The famous case can reveal the process more vividly than a small example. And Boötes does that for void science. It gives us a recognizable anchor for questions that otherwise sound abstract. How do we define a void? How do surveys find one? How large can a low-density region become? What do galaxies inside it reveal? The broader void population also protects the documentary from a false binary. We do not have to choose between fake mystery and total dismissal. We can say voids are expected, then ask why this one is so prominent. Now, some large voids may be connected complexes rather than perfect spheres. That matters because popular language likes clean objects. Science often finds messy structures. A giant underdensity can be made of subregions, ridges, and gradients. So when Boötes appears in a catalogue or discussion, it should be heard as a mapped environment, not a billiard ball of emptiness. Its exact identity depends on how one traces the density field. That sounds technical, but it keeps the wonder honest. We are not making the story smaller by adding definitions. We are making sure the viewer understands what kind of thing can be large enough to deserve a name. And a comparison with other voids gives us a way to judge anomaly. A single dramatic case may feel impossible. A population lets us ask whether the case fits an expected range. Modern cosmology becomes important there. Surveys count and classify voids. Simulations grow virtual universes and compare the outcome. The question becomes statistical, not theatrical. Boötes remains our landmark, but now we can ask whether our best models make landscapes with landmarks like it. The next step is to build emptiness inside a computer and see what kind of universe comes out. A population changes the emotional temperature. Instead of one impossible monster, we see a family of structures. Some are small, some are large, some are complex. Boötes stands out, but it stands out inside a map. Wonder works best this way for GNS. The universe becomes stranger because it is organized, not because it is lawless. And when a famous example belongs to a class, the question matures. We stop asking whether it can exist at all, and start asking where it sits among the others. Modern void catalogues change the frame from legend to landscape. Boötes becomes one named feature in a larger terrain of underdense regions. That larger terrain matters because cosmology is a science of populations. One object can inspire a question. Many objects let us test a distribution. If voids of many sizes appear across surveys, then the existence of a void is not the problem. The problem becomes the range. How large is it? How empty is it? And how often does a structure like this appear? Boötes sits near the dramatic end of that conversation. It's the example the public can remember, and the one that makes the idea of a void feel concrete. But the presence of other voids prevents isolation from becoming exaggeration. We do not need Boötes to be unique in all the universe for it to be worth a long documentary. A famous example can be valuable because it focuses attention. It lets us explain a whole class through one clear case. Now imagine a museum choosing one fossil to explain an entire species. The fossil is not the only specimen, but it has enough clarity to teach the pattern. Boötes works that way for cosmic voids. It's not the whole field, it's an entry point into the field. And because it belongs to a class, we gain a fairer way to judge it. The right comparison is not against our intuition. The right comparison is against void populations in surveys and models. That comparison is where the next part of the evidence lives. The broader population of voids gives Boötes context. Without that context, a famous void can look like a lonely impossibility. With it, Boötes becomes a striking member of a known class. That class does not make it dull. A remarkable example can still teach the process better than a typical one. Fame can be useful when it directs attention toward the right mechanism. So the balance is clear. Boötes is extreme enough to deserve focus, but not so isolated that we should abandon the cosmic web framework. Comparison turns the mystery into a fair test. The phrase extreme not alone should shape our confidence. Extreme keeps the curiosity alive. Not alone keeps the claim grounded. If Boötes were ordinary in every respect, the title would lose force. If it were portrayed as beyond all comparison, the science would become misleading. The real power sits between those errors. A famous void can be a dramatic teaching case while still belonging to a known population. That balance lets the documentary stay calm without becoming flat. Comparison also softens the temptation to make Boötes carry every possible cosmic mystery. It does not need to explain all void science by itself. It can be a landmark. Landmarks are useful because they orient us. From one landmark, the viewer can understand the surrounding landscape. Boötes plays that role here. A simulation gives the question a different kind of pressure. Observers map the sky and ask what is there. Modelers begin with physical rules and ask what kind of universe those rules grow. If the two pictures resemble each other, confidence rises. If they disagree in specific ways, the tension becomes interesting. Now imagine baking bread. The recipe does not only predict the crust and the solid crumb, it also predicts air pockets. If every loaf came out with no holes at all, the recipe would be wrong. If one loaf had a gigantic cavity, you would ask about the dough, you would ask about the oven, and you would check the measurement. Cosmic simulations are far more complex, but the analogy holds. A successful structure formation picture should grow clusters and filaments, and it should also grow voids. The empty-looking parts are not leftovers outside the prediction. They are part of what must be predicted. For Boötes, the most careful question is not whether simulations can make any void. They can. The sharper question asks how often structures of comparable size, profile and sparseness appear under comparable survey choices. Galaxy bias matters here. Galaxies do not mark all matter equally. A simulated matter field may contain structure that a bright galaxy sample traces imperfectly. Comparing map to model means comparing like with like. Void science becomes statistical for this reason. One famous void starts the conversation. A population, a method, and a set of model comparisons decide how much tension remains. The broader population also prevents a false binary. Without comparison, Boötes would have to be either impossible or solved. With comparison, it can be extreme in a measurable family. Catalogues let researchers ask better questions. How many voids appear above a given size? How empty are their centers? How connected are they to surrounding walls? How do results change when the galaxy sample changes? Those questions move the story away from folklore. They let Boötes keep its special role while refusing to make it carry the entire universe on its own. A named void begins the viewer's curiosity. A population tells science what the name means. That population view gives Boötes a fair place. It's not dismissed as one more void, and it is not promoted into a miracle. It becomes a memorable member of a class that can be counted. A simulation can feel like the opposite of a telescope. The telescope receives light from the real sky. The simulation begins with rules and initial conditions. Then it lets a universe grow. Now imagine making bread. The same dough creates the solid crumb and the air pockets. You would not call the holes a failure of the recipe. They are part of what the recipe produces. Cosmological simulations offer a similar lesson. They begin with tiny early density variations, then let gravity work inside an expanding universe shaped by dark matter. Ordinary matter follows that growing pattern over time. The result is not a smooth fog of galaxies. It becomes a network, dense knots, stretched filaments, and the broad, low-density chambers that open around them. That matters for Boötes, because a model does not need a special tier to make underdense regions. The web and void pattern appears naturally when structure grows, but a simulation does not pass just because it makes some empty spaces. The details matter. Astronomers can compare void abundance and size distribution. Density profiles add another test. The galaxies inside low-density regions give the comparison a living tracer. Here is the difference between a slogan and a test. Saying simulations make voids is a start. Asking whether they make the right voids is science. Asking whether the numbers and profiles match is where the test becomes harder, and Boötes belongs inside that larger testing culture. It's a famous example, but the strongest claims come from populations and comparisons rather than one name alone. Now add another complication. Galaxies are biased tracers. They do not mark every bit of matter. A galaxy survey shows where luminous galaxies are found above selection limits. The dark matter field can be smoother, broader, and harder to see directly. That means a galaxy void and a matter void are related but not identical. A region can be poor in bright galaxies without being absolutely empty of matter. Lensing, simulations, and tracer models help connect the visible map to the underlying mass. Think of a city at night seen only through porch lights. The lights tell you where homes are. They do not reveal every road. They miss pipes and fields. They still show the shape of the settlement. Galaxies are extraordinary lights, but they are still lights. So when we compare Boötes with models, we are comparing an observed tracer pattern with a theoretical matter and galaxy story. That comparison is powerful, but it needs care. Fearbait fails for another reason. The dramatic claim asks for one reaction: impossible. The scientific claim asks for measurements instead. It asks how large the void is, how empty it is, and which tracer and definition produced that answer. And those measurements are exactly why voids are useful. They can test galaxy bias and the growth of structure. In broader void studies, they can also pressure test dark energy models and gravity itself. But we should keep the promise narrow. This video is not saying Boötes alone solves those questions. It's saying Boötes helps us understand why emptiness is a measurable part of cosmic architecture. A model that makes emptiness has not explained away the wonder. It has given the wonder a mechanism and a standard of comparison. Now we can ask the hardest version of the question: what would a void have to do before it actually broke our confidence? The simulation point should be heard gently. A model is not a magic stamp of truth. It's a disciplined way to ask whether the rules we think govern the universe can produce the maps we observe. If the rules grow a web with voids that supports the general picture, if the details disagree, the disagreement becomes useful. Either way, emptiness turns into evidence. Voids belong in modern cosmology for this reason. They are not decorative dark spaces between the real objects. They are tests of the whole growth story. A good model has to do more than make beautiful cosmic web pictures. It has to reproduce measurable patterns. Voids are part of those patterns. When simulations grow a network of dense and underdense regions, they show that emptiness can emerge from known rules. That does not end the discussion. It sets the baseline. The baseline lets scientists ask better questions. Scientists can test whether simulated voids are the wrong size, shape, or abundance. They can also ask whether the galaxies inside them resemble observed void galaxies. Those questions turn absence into a precision tool. The quietest regions of the map can test the loudest ideas in cosmology. Boötes by itself should not be forced to carry every test. It's one famous case in a broader comparison between observed galaxy maps and modeled structure. Still, it helps the viewer understand why the comparison matters. If the universe can grow a Boötes-like underdensity naturally, the word whole becomes less useful. If it could not, the tension would become stronger. Now add tracer bias again. Galaxies form where conditions allow them. They do not mark mass in a perfectly neutral way. A model must connect visible galaxies to the darker matter field. That means the map we see is filtered. The filter is not fake, it's part of the observation. We study it because it shapes the evidence. So simulations make emptiness scientific in two directions. They explain how voids can form, and they expose what would count as a mismatch. From there, the question of anomaly becomes more disciplined than any headline can make it. Simulations matter because they ask whether our rules can grow the kind of universe we map. If gravity and dark matter naturally produce void networks, emptiness becomes part of the expected architecture. Expansion and early density variations are part of that same story. The comparison still has to be detailed. The question is not merely whether voids appear, it is whether their sizes and profiles resemble observations. Abundance and galaxy populations add the next checks. Boötes becomes useful for the viewer there. It translates a technical model test into a visible question about one famous sparse region. A model that makes emptiness gives the void a baseline. A model universe is useful because it can surprise its makers. Put in simple starting conditions and known physical rules, then watch complex structure appear. When voids appear in that growth, they stop being embarrassments. They become predictions to examine, but the examination must be detailed. A pretty simulated web is not enough. The profiles and sizes have to be compared with real surveys. Abundance and galaxy content add further pressure. Boötes helps the viewer understand why those comparisons matter in the first place. Models also let us ask counterfactual questions. What if matter had begun smoother? What if gravity grew structure differently? What if galaxy formation traced mass in another way? The answers appear in the voids as much as in the clusters. Sparse regions preserve information about growth because they are less crowded and less processed. That makes them valuable, not empty in the ordinary sense. A real challenge would need more than surprise. Surprise is the beginning of science, not the verdict. For a void to trouble the standard picture, the mismatch would have to survive better data and fair comparison with simulations. Careful selection would be part of that test. Look for the pattern of warnings. Are voids too numerous? Are the largest ones too large? Are their density profiles too empty in the center or too sharp at the edges? Do lensing maps, galaxy maps, and simulations point to different matter distributions? Do the galaxies inside them behave in ways the environmental models cannot explain? Those are stronger questions than asking whether Boötes looks dramatic. They give scientists handles. A handle can be measured and repeated. It can be challenged and improved. Boötes by itself does not carry all that weight. It's an important case, not a one-object verdict on cosmology. Its job is to make the boundary visible between an impressive feature and a broken theory, and this boundary protects wonder. False crisis burns out quickly. A real test lasts longer because it tells us exactly what evidence would change the answer. So when we ask whether the void breaks cosmology, the calm answer is no by itself. The more interesting answer is that voids are among the tools cosmologists use to test gravity and dark energy. In broader work, they also touch neutrino mass and galaxy bias. The growth of structure is the larger test behind both. Boötes opens the door to that testing because it makes absence feel concrete. The challenge is not to shout that the universe is wrong. The challenge is to measure emptiness well enough that the universe has to answer. Model comparison also reminds us that galaxies are not neutral test particles. They form more readily in some environments than others. Gas and stars shape what they show us. Feedback and merger history add another layer. A void in a bright galaxy catalogue may not trace the matter field exactly the same way a dark matter simulation does. So fair comparison often requires making a mock survey from the model. Now apply similar selection rules, count similar traces, measure similar boundaries. Then ask whether the observed void still looks unusual. That step sounds technical, but the intuition is simple. We should not compare a streetlight map with a full census of every road, building and person. We compare streetlights with streetlights, or we translate carefully. Boötes becomes stronger as a science story when those translation steps are visible. The translation also protects against false alarms. A mismatch can appear because the observation and the model are asking different questions. Once the questions are matched, any remaining disagreement becomes much more meaningful. A giant void sounds like a crisis if we treat size alone as the verdict. But science rarely works that way. One dramatic feature is not enough. We need to know what pattern it belongs to. Now picture a car dashboard. One strange flicker might be a loose sensor. Several warning lights, confirmed by different tests, tell you something deeper is wrong. Cosmology has dashboards too. For voids, the warning lights would be specific. One warning would be too many large voids compared with simulations. Another would be density profiles or galaxy populations that fail to match expectations. The strongest warning would be a matter map and multiple surveys, finding the same tension after selection effects are handled. Here is the threshold. Not a headline, not a single striking image. A real challenge would require repeated quantitative mismatch. Boötes by itself does not carry that kind of verdict. It's extreme and important. It's a landmark for the story of mapped absence. But an extreme underdensity is not automatically proof that standard cosmology has failed. And that distinction lets us keep wonder without inflating the claim. We do not have to say nothing to see here. We also do not have to say the universe is broken. We can say this is a strong case study in how large-scale structure should be tested. Here is another courtroom image. A suggestive clue matters. A pattern of evidence matters more. If a void population consistently disagreed with theory beyond expected uncertainty, that would be a case. One famous absence is a witness, not the whole trial. Now consider the sources of apparent tension. Survey selection can miss faint galaxies, and boundary choices can merge or split regions. Redshift distortions can affect maps. Galaxy bias can make matter appear differently through luminous traces. None of those caveats are excuses. They are part of the measurement. A serious anomaly must survive them. Boötes teaches this beautifully because the viewer starts with the strongest intuitive word, whole. Evidence changes that meaning in stages. The apparent whole becomes an underdensity. The underdensity becomes a void, and the void becomes part of a testable population. That progression is the opposite of hype. It does not drain the mystery. It gives the mystery standards, and standards make the final answer more satisfying. If Boötes was simply called impossible, the story would end in fog. If it was simply called normal, the story would end too soon. The truth sits in a better place. Boötes is extreme enough to ask serious questions. It's bounded enough that we should not use it as a physics-breaking claim. So what would actually break? Not emptiness, not scale by itself. What would matter is a durable mismatch between observed void statistics and matter maps. Galaxy populations would have to resist the same comparison. The models that grow the cosmic web would have to fail in a connected way. We are not there with Boötes as a lone object, but because of places like Boötes, scientists know where to look for the difference between an extreme feature and a broken theory. With that threshold clear, the evidence can finally converge. Calm language matters most here. A weak script would pretend uncertainty is panic. A better script lets uncertainty become a measuring tool. Boötes asks us to compare scale and density. Tracer bias matters too. Formation history gives the comparison its direction. Those are serious questions. They do not need exaggerated stakes to matter. The universe is allowed to have extreme features. The scientific question is whether the extremes arrive at the expected rate and with the expected shape. The word anomaly is useful only when we define the test. Otherwise, it becomes a mood. Boötes deserves better than mood. A true challenge would not be simply large, famous, or hard to picture. It would be large in the wrong way, common in the wrong numbers, or structured in a way the model cannot reproduce. It might show a density profile that refuses to match expectations. It might reveal galaxy populations that consistently disagree with low-density environment models. It might conflict with matter maps, not just luminous galaxy counts, and it would need to survive the boring checks. First, the result has to hold when survey depth and selection effects are handled fairly. Then the boundary choice has to remain defensible. After that, redshift distortions and tracer bias still have to be tested against the claim. Those are not excuses, they are the gates any serious claim must pass. The careful answer is stronger than the dramatic one for this reason. The dramatic one gives the viewer a thrill and then leaves them with nothing stable. The careful one gives them a way to judge future claims. Boötes does not need to break cosmology to matter. It matters because it trains our attention on the largest empty-looking structures in the universe. Now we can say something that sounds modest but is actually powerful. Voids are expected, and because they are expected, they can be tested. If a theory predicts no voids, it fails immediately. If it predicts voids with the wrong abundance or structure, it may need revision. If it predicts a population that matches observation, the voids become evidence for the theory's growth story. Boötes, therefore, sits between wonder and standard. It's strange enough to make us ask. It's bounded enough to keep us honest. The best science documentaries live in that place. The anomaly threshold keeps the ending honest. A void becomes a serious problem only when the mismatch survives careful tests across surveys, tracers, and models. Size alone is not enough. A striking name is not enough. The evidence would need to show that the observed void population or matter distribution fails in a way known uncertainties cannot absorb. Boötes does not carry that verdict by itself. It points toward the tests that would matter. That distinction lets the script keep curiosity without pretending the universe is in crisis. This standard protects both science and wonder. It tells us not to panic at every striking feature, but also not to ignore features that consistently resist explanation. A mature anomaly is not a feeling of surprise. It's surprise that survives measurement. Boötes gives us the feeling first. Then the evidence teaches us how to test the feeling. So the final verdict can be strong without being sensational. The void matters even when it does not overthrow the model. A well-defined threshold also protects future curiosity. After this video, the viewer should be harder to fool by a claim that any large void is impossible. But they should also be more interested in genuine void statistics, because those statistics can test real physics. The double payoff is clear. Less hype, more curiosity. Now the evidence can be gathered without squeezing it into a slogan. The map showed a missing crowd. Redshifts gave that shortage depth. The definition turned emptiness into underdensity. The cosmic web gave the underdensity a place in the pattern. Gravity gave it a history. After that, the softer pieces became strengths rather than excuses. The boundary is fuzzy because density changes gradually. The number is approximate because the object is not a solid sphere. The interior galaxies are not contradictions because underdense never meant erased. Boötes survives all of those corrections. In fact, it becomes clearer through them. Each correction removes a false picture and leaves a sturdier one behind. The sturdy picture is this: a vast region of the galaxy distribution where the usual crowd thins dramatically. It forms inside the same web that produces filaments and walls. Clusters mark the crowded side of that same pattern. Now look at what the title has become. The so-called whole is no longer a threat to reality. It's a way of seeing reality's unevenness. The universe is not a smooth spray of galaxies. It's a growing network of contrast, and contrast has two sides. Matter gathering makes bright structure. Matter failing to gather at the same level makes low-density structure. Boötes is the side our eyes are less trained to see, so the final answer can be calm and still feel large. We do not have to inflate Boötes into a tear in space. The truth already stretches hundreds of millions of light-years across the map. The anomaly threshold also has an emotional purpose. It keeps us from wasting the viewer's curiosity on a fake cliff. The real cliff is more precise. Does the universe produce the right empty structures for the right reasons? If future surveys and simulations found a persistent mismatch in void populations, that would matter. It could point toward missing physics or misunderstood galaxy bias. Survey systematics would have to be checked, so would the way structure growth is modeled. But the standard for that claim is high because the claim is important. Boötes can motivate the test without becoming the whole result. That distinction is mature science. It lets us be excited by an extreme feature and honest about what one feature can prove. The anomaly question should feel less like a verdict and more like a measuring instrument. Boötes helps tune the instrument. The broader void population does the heavier statistical work. Return to the first image, a map in the direction of Boötes. A crowd of galaxies that should continue, then thins across a vast region. Now the picture is different. We are no longer staring at a hole, we are reading a structure. The map became meaningful when the galaxy census showed scarcity against the surrounding regions. Redshift mapping then gave that scarcity depth, so the apparent gap became a volume problem rather than a flat patch on the sky. The definition changed the emotional shape of the story. A void is not nothing. It's an underdense region that can still contain galaxies, gas, dark matter, and smaller internal structure while remaining sparse compared with the cosmic average. The cosmic web gave that underdensity a home. Crowded walls and stretched filaments are not separate from the quiet chambers between them. Gravity amplifies tiny early differences, so matter gathers into brighter regions while other regions fall further below the mean. The famous number belongs inside that measured picture. Roughly 300 million light-years gives scale, not a polished edge, and the boundary still depends on definitions, surveys, and tracer choices. Galaxies inside the region do not defeat the void. They help show the difference between absolute emptiness and genuine underdensity. Comparison keeps the conclusion from floating away. Boötes is extreme and historically memorable, but modern surveys place it among a wider population of voids. Simulations explain why web and void networks should grow, while the anomaly threshold asks whether abundance, size, and matter mapping ever disagree in a durable way, so the answer has shape now. Boötes is real as a mapped underdensity, and it is extreme enough to matter. It is not absolutely empty, and it is not a portal, tunnel, or tear in spacetime. By itself, it is not proof that our picture of the universe has collapsed. But it is not trivial either. It's one of the places where the universe teaches us that structure includes negative space. The map is made not only by bright strands, but by the vast rooms between them. Here is the final mental image before we close. Imagine the cosmic web as a cathedral made of dark matter and galaxies. The filaments are the arches, the clusters are the joints, the voids are the chambers. Take away the chambers and the architecture no longer makes sense. Boötes is one of those chambers, enormous, sparse, bounded by evidence, and much more interesting than a literal hole. Here is the convergence we needed. Not one slogan, but a sequence that changes the picture. The galaxy counts reveal the shortage. The distance map gives that shortage depth. The web and void framework then explains why a real structure can be defined by scarcity rather than brightness. By the time the scale is tested, the word whole has already become a measured underdensity. Each step removes a false picture and leaves a stronger one behind. By the end, Boötes is not less strange, it's more intelligible. And intelligible wonder lasts longer than shock. It gives the viewer something they can carry into the next map of the universe. The chain of evidence also explains why the title works. The phrase "hole in the universe" captures the first impression. The documentary earns the right to replace it. At the start, we had a missing crowd on a map. Distance turned that impression into volume, and underdensity gave it the right physical name. From there, the cosmic web and gravity supplied the mechanism. The remaining details, soft boundaries, sparse internal galaxies, and comparison with wider void populations, made the answer steadier rather than louder. Each layer changed the meaning of emptiness. The word became less literal and more informative. By the time we return to Boötes, the void no longer feels like a blank. It feels like a room whose walls are made by the surrounding distribution. That room is not empty in the absolute sense. It has a sparse interior and soft edges. It has a history, and it has a place in the cosmic web. It also has a lesson about evidence. The universe can be mapped by what is present and by what is scarce. Both kinds of information matter. Negative architecture is the right final frame for this reason. The void is not a failure to find structure. It's structure seen from the low-density side. Now the opening image has transformed. The thinning map is not a scary absence. It's a signature of how gravity, time, and initial conditions made a lumpy cosmos. Boötes remains extreme. It remains worth attention, but its power comes from being real and bounded, not impossible. And that gives the closing a clear answer to the viewer's first question. The convergence matters because the answer has been assembled rather than asserted. Boötes began as a missing crowd. It gained depth through redshift. It became an underdensity through definition, then found its place inside the cosmic web. Gravity supplied the growth story. Measurement limits softened the title number. Interior galaxies gave the sparse region texture. Catalogues and simulations gave it comparison. The final picture is therefore stronger than the first impression. The void is not less strange after correction. It's strange in a way the evidence can support. Absence has architecture. The convergence also reveals why the topic belongs to long form. A short explainer can correct the word whole. It cannot let the viewer travel through the whole evidence chain. Here the chain is the payoff. The viewer begins with a simple impossibility and ends with a map of structure formation. That journey respects the click without exploiting it. It says, yes, the region is astonishing. No, the cheap version is not enough. And that leaves Boötes where it belongs, as a serious piece of the cosmic web rather than a scary blank in the dark. By now, the answer is not a single sentence but a structure in the listener's mind. Boötes is mapped scarcity. It is three-dimensional evidence, and after all the mythology is stripped away, it is a bounded anomaly inside a cosmic web that can be measured. That layered answer is why the void can stay mysterious without becoming misleading. The universe did not give us a simple whole. It gave us something more useful, a way to study how absence becomes part of form. The convergence also changes how we imagine maps of the universe. A good cosmic map is not just a collection of bright islands. It's a record of relationships where clusters connect through filaments and walls help define the voids beside them. Boötes teaches that the quiet parts of that map are not empty of meaning. They carry information about initial conditions and gravitational growth. Survey limits matter too. Galaxy formation is part of the same record, so the phrase "absence has architecture" is not a decorative ending. It's the argument compressed into one image. The architecture includes the bright beams and the open rooms. Without both, the building cannot be understood. Now the closing can return to the viewer's first question without needing another detour. The answer has been earned by the map and the method. Definition, mechanism, and boundary do the rest. By the time we reach the final answer, the word whole has changed jobs. It no longer describes the physics, it describes the viewer's first impression, the picture we had to refine. Before we leave the body of the evidence, one final distinction keeps the answer from becoming too neat. Boötes is not meaningful only because it is sparse. It's meaningful because its sparseness can be placed inside several independent ways of knowing. Galaxy positions give the visible census, and redshifts give it depth. Void definitions set the density threshold, while cosmic web maps give the result context. Formation theory, simulations, and interior galaxies then connect Boötes to a wider physical story, rather than leaving it as a lonely curiosity. None of those alone has to carry the whole story. Together, they make the void hard to dismiss and hard to exaggerate. We want that balance. A single strange map can become folklore. A single tidy explanation can become boredom. Boötes sits between those traps. It's strange enough to hold attention, and measured enough to keep the narration honest. Now picture the cosmic web as a building seen at night. The lit corridors are easy to follow. The rooms without lights are harder to read, but they still tell us where the walls are. They show where corridors end. Boötes is one of those dark rooms on an almost unimaginable scale. The room is not outside the building. It's not proof the building has failed. It's part of the plan left by gravity and expansion. Initial conditions and time finish the shape, and because it is part of the plan, it can teach. It teaches that galaxies are tracers, not the whole universe. It teaches that a famous number may be approximate and still important. It teaches that an extreme feature can invite real tests without becoming a crisis by itself. So the convergence should feel settled, but not flattened. We have not explained away the wonder. We have moved the wonder to the right place. The right place is not a literal whole. It's the fact that absence, when measured carefully, becomes one of the largest forms of cosmic structure we can name. One last practical result follows from that. When a viewer hears whole, the first instinct is to look for an object. The evidence teaches a different instinct. Look for a distribution. Ask what was counted. Ask how far away it is. Then ask how the density compares with the web around it. That habit is portable. It works for Boötes, and it works for other cosmic mysteries where a simple image hides a deeper map. The same habit keeps the closing honest. We do not need every uncertainty solved to know what kind of thing Boötes is. We need enough linked evidence to say which picture has failed. The literal whole picture has failed. The underdense region picture survives, deepens, and connects to the rest of cosmic structure. The answer satisfies because it changes the question rather than dodging it. The universe did not leave a blank because something punched through it. It left a low-density region because structure formation creates contrasts so large that even absence becomes mapped. The repair to the viewer's first image is now complete. We began with an enormous apparent gap. We tested whether the gap was only a picture, then whether it was absolute emptiness, then whether it belonged inside known structure formation. Each test made the claim less theatrical and more durable. Good evidence often does that. It removes the wrong kind of drama and leaves the better kind behind. Boötes no longer needs to be impossible. It's more interesting as a real underdense region that forces us to think about maps and gravity. Galaxies and cosmic history complete the picture. So the answer has weight because it was not handed to us in one sentence. It was assembled from compatible pieces, each one narrowing the meaning of the so-called whole. So why is there a 300 million light-year hole in the universe? The clean answer is this: because the word hole is only a doorway. The Boötes Void is not a tier or a tunnel. It is not a missing piece of space-time, and it is not a black object hiding between galaxies. It's a vast, underdense region in the galaxy distribution, a place where the expected crowd of galaxies thins across an enormous volume. And once we say that clearly, the mystery does not disappear. It becomes more physical. We can now see the chain without turning it into a checklist. Astronomers first found a dramatic shortage of galaxies, and redshift surveys gave that shortage depth. Better definitions then corrected the false picture of perfect emptiness. A void can still contain galaxies, gas, and underlying matter, while remaining genuinely sparse. The cosmic web gives Boötes its home, because crowded clusters and low-density chambers are parts of the same architecture. Wider void populations show that Boötes is extreme rather than alone, and gravity explains how tiny early differences could grow into bright strands beside broad, quiet regions. That's the answer the title was hiding. Boötes exists because the universe did not grow smooth, it grew contrast. Some regions gained matter and became the bright architecture we notice first. Other regions fell below the average and became the architecture of absence. So Boötes is real. It's extreme, it's historically important. It's useful because it lets us study the universe from the side of what did not gather. But it is also bounded. By itself, Boötes does not prove that cosmology has broken. A true crisis would require a deeper mismatch. Void sizes and abundances would have to refuse the models. Density profiles, lensing maps, or galaxy populations would have to fail after fair comparison with surveys and simulations. The famous emptiness is evidence, not a verdict shouted ahead of the evidence. That boundary matters. It keeps the wonder intact. The universe is strange enough without turning every strange feature into a crisis. By now, the first picture should look different. At the beginning, a hole sounded like a place where the universe failed. Now it looks like one of the places where the universe reveals how it was built. The emptiness has shape because matter has history. The sparse region has meaning because the surrounding web is crowded. The few galaxies inside the void matter because they show that low density does not mean unreal, and that may be the deepest lesson of Boötes. We often understand the cosmos by following light. Stars shine, galaxies glow, clusters announce themselves. But some of the largest structures are understood by following where the lights are missing. A map of the universe is not only a map of presence, it's also a map of absence measured carefully enough to become knowledge. So the so-called whole is not the end of the story. It's an invitation to read the cosmic web in both directions, by the filaments that gather galaxies, and by the voids that show where the gathering did not happen. Once we learn to see that, other questions open naturally. If a vast underdensity can hide in plain sight a structure, what else does the large-scale map contain that we only partly understand? What pulls galaxies toward the great attractor? Where is the missing normal matter spread through the web? How much of the universe's architecture is written not in bright objects, but in the spaces between them? For tonight, Boötes gives us one clear answer. The universe does not have a literal 300 million light-year hole punched through it. It has a giant, underdense chamber in the cosmic web. Gravity shaped it, galaxies measure it, and it matters because absence itself can have structure.